Hi, this is John Whitaker for the Mathematical Analysis 2 class, and this is our 31st video lecture. And today we're going to have an extended lecture. I'm going to go over only two theorems, one of which, the first one, has two parts to it. It's going to be related to pointwise boundedness, equicontinuous functions is what we're going to be looking at with the sequence, and we're going to say something about them in terms of subsequence. And also we're going to look at something called the Weierstrass theorem, which has to do with approximating continuous functions with polynomials. And so without further ado, let's go ahead and get started. So the first theorem has got two parts. Here's what it says. It says if K is compact, if f sub n is an element of C of K, remember those are complex value functions that are continuous and bounded, and that's true for n equals 1, 2, 3, whatever. And if f sub n is the collection of pointwise bounded, and equicontinuous functions on K. Okay. Then we have two parts. Part A, then the first part is f sub n is then uniformly bounded. On K. And then the second part, part B, is that f sub n contains a uniformly convergent subsequence. Okay. Okay, so that's what we want to prove. Okay, well, for our proof, let us assume the conditions. K is compact, so let K be compact. Okay. F sub n be an element of C of K. For n equal 1, 2, 3, forever. And F sub n, we're going to let them be pointwise bounded. And an equicontinuous family of functions. Okay. Okay, for part A, where we're trying to show uniformly boundedness, what we're going to do is we're going to let epsilon be equal to 1. Since f sub n are equicontinuous, okay? Collection of equicontinuous functions. Okay. Then there exists a delta bigger than 0 such that for all x y element of k with the distance between x and y being less than delta, then absolute value of f sub n of x minus f sub n of y, that is going to be less than 1, which was our epsilon here, and that's true for all n. Okay. Now consider the collection of subsets of K so these are neighborhoods with radius delta centered at X. And this is true for all, this collection runs for all x's in K. Now, where, just as a reminder for what a neighborhood is, n sub delta of x is equal to all the y's element of K such that the absolute value, or the distance, between x and y is less than delta. Then when you look at these neighborhoods, this collection over all x's in K is an open cover. For K, and since K is compact, by definition, compactness, it has a finite subcover. Has a finite subcover. Okay. Thus, there exists a finite subcollection. I just should say a finite collection of points. Okay, that's what I'm going to do. Okay, in K. And let's give them some notation. So here, x1, x2, all the way up to x sub p. Such that these collections of neighborhoods centered at x sub I, okay, where I runs from 1 up to p, covers K. Now, since f sub n is a collection of pointwise bounding, then for each x sub 1, x sub 2, all the way up to x sub p, there exists an m x sub I, that's a number, such that the absolute value of f sub n x sub I is going to be less than or equal to m sub x sub I. And I only got finitely many of these m sub x sub i's. And this is true for all n. Okay. So we're going to just pick the biggest one of these m sub x sub i's. Let me write that down. Okay, so we're going to let m be equal to the maximum of m sub x sub 1 with m sub x sub 2 all the way up to m sub x. I think we had p up. Yes. Then what we've got is the absolute value of f sub n of x sub I will be less than or equal to m. Okay, and that's true for all of I equals 1, 2, up to p, and for all n. Now what we're going to do is we're going to let y, just an arbitrary point in k. Then, because we had this finite subcover, y has got to be an element of one of these neighborhoods about these x sub i's. Some I equal to 1, 2, all the way to p, one of them. Okay. And because you're in this neighborhood, that means that the distance between y and this x sub I is less than delta. So, what that tells us is that the absolute value of f sub n of y minus f sub n of x sub I, that's going to be less than 1, or epsilon, and that's true for all n, and that's due to the equicontinuous. That's the collection of the functions of s sub n's. Okay. Now, something that's smaller than this is the absolute value of f sub n of y minus the absolute value of f sub n of x sub I. Okay. So what I just wrote is smaller than what's above, and so since what's above is less than 1, the smaller thing has to be less than 1, and that's true for all n. Working with that inequality, we get that minus 1 is less than or equal to the absolute value of f sub n of y minus the absolute value of f sub n of xi, which is less than or equal to 1. And that's true for all n. And it's not less than or equal to, it's just less than. That's true for all n. So solving for f sub n of y inside absolute value, we have minus 1 plus f sub n, absolute value of f sub n of x sub I is going to be less than absolute value of f sub n of y. which is going to be less than 1 plus the absolute value of f sub n of x sub I. Again, that's true for all n. Okay? Okay. So here, that means that the absolute value of f sub n sub y is going to be less than 1, and I'm going to replace this with something bigger. What's bigger than that is m. So, and this is true for all n and for all y element of k. So here, this is my uniform bound for this sequence. This is a proof that I had, a statement and proof that I had mentioned that I'd like for you to know for test 2. So let's become aware of that proof. Now, for part B, we're trying to create a subsequence of the f sub n, which is uniformly convergent. Okay, so we're going to start with that. That's just a reminder of what we need to do. This is going to be done because we're going to start off with K being compact. So since K is compact, I'm about to write down a fact that we haven't proven but it's true. And really, it's a homework assignment in the book, but we're not going to be assigned it. Then K has a countable dense subset. Again, let me write down, we have not proven this, but it is true. And let's call that dense subset, countable dense subset, E. Now, since f sub n is pointwise bounded on K, pointwise bounded on E, okay, then by a previous fact, f sub n has a subsequence f sub n sub I, okay, such that f sub n sub I of x converges. And that convergence happens for each x in E. Again, this is due to a previous result we had where we had these sequences we formed with S's, you might remember in the proof. Anyway, to simplify notation here, we're going to let F sub n sub I just be equal to G sub I. That's the way I want to define it. To simplify the notation. Now we're going to let epsilon be greater than 0 be given. Okay. Since the f sub n's are equicontinuous, they're equicontinuous, okay? Then the sub sequence, the G sub i's, they are equicontinuous. Okay. So that means, by definition of equicontinuous, that there exists a delta greater than 0 such that for all x and y, element of k, with the distance between x and y being less than delta, then the absolute value of g sub I of x minus g sub I of y will be less than anything I want. I'm going to choose epsilon over 3, and this is true for all i's. All right. Now note again that this collection of neighborhoods of radius delta centered at x, where x is known as k, is an open cover for k. Since E is dense in K, that means that every neighborhood of any x in K contains a y from element to B. Then, okay, and K is compact. Okay, there exists a finite number. I'm skipping some details here. So a finite number of points from E. So that's the from E part that I want to emphasize. Say, here I'm going to call them x sub 1, x sub 2, all the way up to, let's say, x sub m. Okay. Such that, get this finite subcover. So K will be contained in n sub delta of x sub 1 union the neighborhood greater delta about x sub 2 union so forth up to the union n sub delta of x sub m. Now, since the G sub i's converge, and this is pointwise conversion. So this converges for each x in E. Okay. There exists an integer n sub x sub q such that for all I and j bigger than or equal to n sub x sub q, the absolute value of g sub I of x sub q minus g sub j of x sub q will be less than epsilon over 3. And this is for q equaling 1, 2, all the way up to m. So we're still using those particular finite collection of the x sub i's here. I'll just relabel these x sub q's. Now, that means we only have finitely many of these n's. So we're going to let big N equal to the maximum of n sub x sub 1, n sub x sub 2, all the way up to n sub x sub 3. I'm sorry, x sub m. Then for all I and j being bigger than or equal to n, what we have is that the norm of g sub I x sub whatever, q, minus g sub j of that same x sub q, that's going to be less than epsilon over 3, and that's true for any q equaling 1, 2, all the way up to m. Okay. Now we're ready to show the uniform convergence. So here we're going to let x be an element of K. Then what I know is that x is in one of these neighborhoods, about an x sub q. Okay? For some q equaling 1, 2, all the way up to m. Okay. So that g sub I of x minus g sub I of x sub q will be less than epsilon over 3. And this is due to the equicontinuousness of the g's. And this is true for all I. Okay. So for all I and j bigger than or equal to n, we look at this g sub I of x minus g sub j of x. Okay. Now I'm trying to show uniform convergence here. So I want to show you this is less than epsilon we've been given. Using the Cauchy criteria is what I'm doing. So that guy can be rewritten as the absolute value of g sub I of x. Okay, now I'm going to add and subtract some things. Minus g sub I of x sub q plus g sub I of x sub q minus g sub j of x sub q plus g sub j of x sub q, and then minus the g sub j of x, which can be split up using the triangle inequality as g sub I of x minus g sub I of x sub q plus g sub, I of x sub q minus g sub j of x sub q plus the absolute value of g sub j of x sub q minus g sub j of x. Okay. And due to the equicontinuous nature, this guy is going to be less than epsilon over 3. This guy, due to the convergence, is going to be less than epsilon over 3. And then here, due to the equicontinuousness of the g sub j's, this is going to be less than epsilon over 3, which equals to epsilon. So, by the Cauchy criterion for uniform convergence, the sequence g sub I is converged uniformly. On K. And that is that proof. Okay, the next theorem we're going to look at is due to Weierstrass. And here's what he says. It says if f is a continuous, complex function on the closed interval a to b, there exists a sequence of polynomials I will call P sub n such that the limit as n goes to infinity of the P sub n's equal to f uniformly on a to b. Now, if f is real value, instead of being complex, then the P sub n's will be real. May be taken as real. That's kind of nice. So we're saying any continuous function can be approximated through uniform convergence by a sequence of polynomials. That's kind of nice. Polynomials are nice to work with. Okay, so let's look at the proof. We'll break the proof into a couple of cases with some sub-cases. One case. So here's case one. The proof is long. Here we're going to assume A to B is equal to 0 to 1. And we're going to extend it from this eventually. So sub-case 1 is suppose f of 0 is equal to f of 1, which equals to 0. So for our function that's continuous, we've got these two endpoints equaling to 0. So with, of course, we're saying f being continuous. On 0 to 1. Then we're going to extend f of x. Then define f of x to be equal to 0 for all x not in 0 to 1. Now, since f is continuous, on 0 to 1, it's uniformly continuous. Continuous. On 0 to 1. But that uniform continuity is going to extend to the whole real line because of the way we're defining f. Let me write that down. Since f of 0 equals to f of 1, which equals to 0, and f of x equals to 0 for all x not in 0 to 1, okay, then f is uniformly continuous on R. So what we're going to do is we're going to find something q sub n of x. What we're going to find it to be is c sub n, some number, times 1 minus x squared raised to n, and that's true for n being equal to 1, 2, 3, forever. And c sub n is chosen so that the integral from minus 1 to 1 of q sub n of x dx, the Riemann integral, is equal to 1. And that's true for all n elements of natural numbers. Okay? So I want you to also note something about q sub n of x. Well, q sub n of minus x. So here, if you replace x by minus x, when you square it, you're going to get the same thing as q of x. So that means that it's an even function. Is an even function. Okay. So that means, I'm sorry, so q sub n of x is symmetric about the y-axis, and that tells me something about this integral. Okay. So the integral from minus 1 to 1 of q sub n of x, well, let me just write it down instead of q sub n. Let me just talk about 1 minus x squared raised to n, that part of q of x, dx. That's going to be equal to 2 times the integral from 0 to 1 of 1 minus x squared raised to n dx. Now I want to tell you that's going to be greater than or equal to 2 times the integral from 0 to 1 over the square root of n times 1 minus x squared raised to n times d of x. Okay? So here it's because that 1 minus x squared raised to n for x is in between 0 and 1, that's going to be a positive number, and so the integral is always going to be positive, so I'm not integrating over as big of a region, so I got something that was smaller. And that's going to be less than or equal to 2 times the integral from 0 to 1 over the square root of n. And now I'm going to replace the integrand with something smaller. And what I'm going to replace it with is 1 minus n times x squared dx. And this comes from the fact, so let me write this down here, just as a fact, that 1 minus x squared raised to n is bigger than or equal to 1 minus n times x squared, which can be proven using induction. I'm not going to prove it. Okay, so we're going to do that integral now. This is equal to 2, and when you integrate this, you're going to get x minus n x to the third over 3. We'll evaluate that from 0 to 1. Okay, and 0 to 1 over the square root of n. Okay. And that's going to be equal to 2 times 1 over the square root of n, okay, minus, here this would be n times 1 over the square root of n, raised to the third power over 3. When we stick in 0 for x, we're just going to get 0. And that's equal to 2 times 1 over the square root of n, minus, here I'm going to get 1 over 3 times the square root of n. And that's just equal to, with the common denominator, 2 times, this would be 3 minus 1 over 3 times the square root of n, which is equal to 4 thirds square root of n. Okay? And that's definitely greater than 1 over the square root of n. Okay. Thus, what that's going to tell us is something about c sub n. For the integral from minus 1 to 1 of c sub n times 1 minus x squared raised to the n dx to be equal to 1, that says that c sub n, okay, has to be less than the square root of n. So, for any delta here is bigger than 0 but less than or equal to 1, then for all x with delta less than or equal to the absolute value of x, which is less than or equal to 1, then q sub n of that x, which is equal to c sub n times 1 minus x squared raised to the n. Okay, so I'm replacing this with this x. I'm going to replace this x with delta. So this is going to be less than or equal to c sub n times 1 minus delta squared. So here, I'm replacing the x with the delta. When I square it, I'm going to get something smaller than what I would get with x. So I'm taking from one something smaller, so it got bigger, raised to the n power, okay, which is less than or equal to the square root of n. Remember, this guy is less than or equal to the square root of n, times 1 minus delta squared raised to the n. Okay, now note the limit as n goes to infinity of the square root of n times 1 minus delta squared raised to n, which if you work with this is going to be an infinity times 0, indeterminate limit form. So we rewrite it as the limit as n goes to infinity of 1 minus delta squared raised to the, we're going to put the square root of n at the top and go 1 minus delta squared raised to the minus n in the bottom. Okay. Now, this ends up being an infinity over infinity form, and so we can use L'Hopital's rule. And so this is the limit as n goes to infinity. This is going to be minus, so it's going to be 1/2, and then we're going to have the square root of n, or the n raised to minus 1/2. That's the square root of n here in the bottom. Okay? And then we have to take the derivative of 1 minus delta squared, all that raised to the minus n. And we're taking the derivative of it with respect to n. And the way that we do that is through what's known as logarithmic differentiation. I'm not going to go through with that with you. I'm going to tell you here's its answer. It's 1 minus delta squared raised to the minus n. Okay, and then it's ln of 1 minus delta squared, and then times minus 1. That's what we get. Okay? And that's equal to the limit as n goes to infinity of 1 over 2 times square root of n times 1 minus delta squared raised to the n. I'll bring that part to the top. Over minus ln of 1 minus delta squared was just a number. And so this goes to 0. And that's for all 0 less than delta is less than 1. When delta is 1, we get 0. So what that means is there exists a natural number n such that for all n bigger than or equal to big N, the square root of n times 1 minus delta squared raised to the n will be less than epsilon. Thus, for all n bigger than or equal to big N, what we have is the absolute value q sub n of x minus 0. Okay? That will be less than epsilon, but not for all x, but for the ones for x's such that for all x's such that the delta is less than or equal to the absolute value of x, which is less than or equal to 1. Oh. Now, what we're going to do is we're going to let p sub n of x, this is our polynomial, it's going to be from minus 1 to 1 of f of x plus t times q sub n of t dt, and that's what we're going to find it to be for x is bigger than 0 and less than 1. Run here. And so here's what I want to do. I want to tell you that since f of x is 0 outside of the interval from 0 to 1, then f of x plus t is possibly non-zero. Okay? Only when 0 is less than x plus t is less than or equal to, it's less than or equal to, well, it's less than 1, you can say less than or equal to, but you can say less than, because when it's equal to 0 or 1, we did get f evaluated, that was 0. So here, f of x plus t is only, or is possibly non-zero when minus x is less than or equal to t, which is less than or equal to 1 minus x. So p sub n of x really is going to be equal to minus x up to 1 minus x f of x plus t q sub n of t dt. And then using a change of variable, particularly u is equal to x plus t, we have P sub n of x will be equal to so here it would be 0, that's what you would run, up to 1 of f of u, and here this would be q sub n of, here it would be, when I solve for t, be u plus x, or u minus x, my mistake. And then this would be du. Okay. So, one more time about p sub n. P sub n of x will be equal to the integral from 0 to 1 of f of u c sub n times 1 minus, here this will be u minus x to b squared raised to the n du. And this quantity right here, the u's what's changing, but this is going to be a polynomial in terms of x. So I just wanted to make sure that p sub n of x was a polynomial in terms of x, and that's what all this last work we've been doing gives us. I do want to make one more comment, and that is, and if f is real, then p sub n of x is real for all n. Okay. Now, we want to work on the convergence. The uniform convergence. We let epsilon be greater than 0 be given. Okay. Since f is uniformly continuous, okay, we can choose delta bigger than 0, such that for all x and y element of a to b with the value of x minus y being less than delta, then f inside absolute value of x minus f of y, that's going to be less than, well, whatever I'd like is positive, and I'm going to pick epsilon over 2. Excuse me. We're going to let m equal to the supremum of the f of x, which we know exists as f is continuous on a compact set. That compact set was from 0 to 1 in this case. Excuse me. Now, for every x with 0 less than or equal to x less than or equal to 1, we have that's the value p sub n of x minus f of x. Definition p sub n of x.
excuse me, is the interval from minus 1 to 1 of f of x plus t q sub n of t dt, okay, minus f of x. But f of x is f of x times the interval from minus 1 to 1 of q sub n of t dt. Okay, which can be rewritten as an interval that's the value of the one interval, minus 1 to 1 of f of x plus t minus f of x all times q sub n of t dt, which is less than or equal to, bringing the absolute values inside, the interval from minus 1 to 1, f of x plus t minus f of x. Now, it would be the absolute value of the q sub n, but that's positive, so it's q sub n of t dt. And then this can be split up as the interval from minus 1 to delta, minus delta, of f of x plus t minus f of x, inside absolute values, q sub n of t dt, plus the interval from minus delta to delta of f of x plus t minus f of x, I'm sorry, yeah, it's f of x, that's right. And then q sub n of t dt, plus, I'm going to write right here, interval, and it's going to be from delta to 1 of f of x plus t minus f of x inside absolute values times q sub n of t dt. I know it's not very nice, but it's easy to understand. And we're going to get that each one of these guys can be made real small. Okay. Now that first interval is going to be less than less than or equal to, so let's substitute something in bigger. That distance between f of x plus t and f of x, that distance is going to be less than 2m, where m was that supremum. And then I have the interval from minus 1 to minus delta of q n sub t dt. Plus that next interval, that middle interval we had, because we're talking about in between the deltas here, we have, well, that's going to be less than epsilon over 2 times the interval of q sub n of t dt, and that's from minus delta up to delta. And that's because the input values, x plus t, and that distance from x, because t runs from minus delta to delta, those distance between those input values is less than delta. And so that's why we get that the absolute value of the differences between the output values are less than epsilon over 2 by our previous work. Plus, this is 2m again for the last interval from delta to 1 of q sub n of t dt. We had something about those intervals. So it's less than or equal to 2m. And so for this interval, this is the less than, what I'm going to put in something bigger, is the square root of n times 1 minus delta squared raised to the n. that's a constant, plus epsilon over 2 times something bigger than this is 1, because the integral of the q sub n from -1 to 1 is equal to 1, so I'm putting in something bigger. Plus 2 sub m, and substituting something bigger in for here, it's going to be the square root of n times 1 minus delta squared raised to the n. And that's what I have. Now, since, as we've shown, that the limit as n goes to infinity of the square root of n times 1 minus delta squared raised to n equals to 0, we've shown that. There exists a natural number such that for all n bigger than or equal to this natural number, okay, for m times the square root of n times 1 minus delta sub squared raised to the n, which I'm looking at this part right here, will be less than epsilon over 2. So, here's what we get. For all n greater than or equal to n, the norm of p sub n of x minus f of x will be less than epsilon. So what this says is, so p sub n converges uniformly to f of x. Now, we got a subcase 2 here, but we don't have very much more to go, okay? So subcase 2, what we're going to be considering are situations that we can relate to subcase 1 here, okay, of case 1. So subcase 2 is if f of 0 is not 0, or if f of 1 is not equal to 0, consider the function g of x equaling to f of x minus f of 0 minus x times f of 1 minus f of 0. Okay. And now you can see that g of 0 is equal to 0, and g of 1, you just take it as easy, is equal to 0. So by our previous work, okay, subcase 1, so g is obtained by a limit of uniformly converted sequence of polynomials p sub n. Thus, f is obtained by a limit of uniformly convergent sequence of polynomials we call them P sub n plus f sub 0 plus x times f sub 1 minus f sub 0. That's great. We got another case. So remember, this first case was based on a to b being equal to 0 to 1. Well, the next case is looking at that. We are almost done. Suppose a is different from 0 or b is different from 1. We define g that goes from 0 to whatever b minus a is by g of x is equal to m of x plus a. Now define L from 0 to 1 by L of x is equal to g evaluated at b minus a times x. Then, so L is defined from 0 to 1, so L is the uniform limit it's the limit of uniformly converging uniform convergent sequence of polynomials we'll call it p sub n of x. On 0 to 1. So G is the limit of uniformly convergent sequence of polynomials. I'll call it P sub n star equal to P sub n evaluated b minus a times x on 0 to b minus a. Thus, F is the limit of uniformly convergent sequence. functions. Okay. Of polynomials, not just functions. I'll call it, oh gosh, I've run out of room. P sub n double star of x, which equals to P sub n star evaluated at x plus a. That is the proof.
Ladies and gentlemen, that's more than enough for today. Thank you very much for your time and patience.